All right, last time we started talking about waves in general, and where we left off was on this video, I think. And it was just generically talking about the different types of waves, like transverse waves and longitudinal waves, and what the wavelength is and what the frequency is. And we're going to talk about waves all class. Why? Because, well, pretty shortly, we're going to get into transmission lines and the waves propagating on transmission lines. Since we're going to be talking about waves on transmission lines so much, we want to be able to mathematically describe them. And we're going to start by talking about lossless waves, meaning that it doesn't matter how long the wave travels, it never gets weaker and weaker and weaker. It just always maintains its same strength, whether that's power level or voltage amplitude, or in terms of water, it would mean wave height, like the wave doesn't get kind of like weaker and weaker as it travels. So that's what we're going to talk about all tonight. And what's the best way to talk about waves when we're going to talk about the math behind them? Well, I think it's probably water waves, because we've all seen lots of water waves before. And so on the top right, we have a picture of waves on a lake. Bottom right, we have pictures of waves in a wave pool. How are we going to mathematically describe a wave? Well, a good way to do it would be with a sine or cosine function, right? So let's just remind ourselves here, what's a sine? Well, sine starts at 0. Okay. So this is sine. And what's a cos? Well, cos starts at 1. That's the only difference between them. It's a phase shift of 90 degrees. We could do everything in terms of sines, but we're going to use a cosine reference for everything. So we're going to do everything in terms of coses. Okay, well, what does a cos go up to? Well, if it's just a plain old cos, its peak is +1 and its minimum is -1. And if you don't believe me, just grab your calculator. If it's in degree mode, put in the sine of, or let's say cos, put in the cos of 0 and you'll get 1. Put in the cos of 90 degrees and you'll get 0. Put in the cos of 180, you'll get -1, right? Go all the way, put in the cos of 360 degrees. Now you've gone a full cycle and you're back to +1. So 360 degrees is a complete cycle. You could think about it as a rotation around a circle, or you could think about it as a wave where the wave has completed an entire cycle and is back to where it started. Okay. We're going to normally deal with radians though. We'll go back and forth. So make sure you can go back and forth between degrees and radians. Whenever you see like a 2 pi though in a formula, that's a good sign you're in radians. And so you should do things in radians, and you should make sure your calculator is in radians. So what's a complete cycle in radians? It's 2 pi. So a complete cycle is 2 pi radians. All right, so let's talk about a wave. All right, so let's say we are in this pool. There you are. It's my highly accurate drawing of you in this swimming pool. And I have given you a big ruler. And you're going to measure the height of the water wave. All right. What is the height? Well, we are going to represent the height as y. Now, imagine the waves are just kind of like, they keep coming, right? The waves just keep coming down the pool, down the pool. And the height of the wave, well, it's going to depend on 2 things. It's going to depend on where are you in the pool, right? Because you could be, well, maybe you're back here, or maybe you're up there. We're going to call that x. We're only going to look like kind of like front to back. Side to side, you can see it's the same everywhere because the wave is the same all the way across, like kind of into your screen and out of your screen. So we're just going to worry about kind of the left to right. We're going to call that x. And then it also matters what time it is, because the waves just keep coming, right? And so in order to know the height of the wave, you would need to know where are you in the pool, like what's your value of X, and you would need to know what time is it. So if you froze time, like this picture is frozen in time, we've kind of fixed T, right? And if you froze in time, and it's like one of those movies where you can freeze time, but you can still walk around and like, do stuff. Well, if you froze time, but then you could walk left and right in the X direction down the pool and make different height measurements of the wave, what you'd be doing is you would be figuring out what the height is in terms of X at a particular time T. Or you could fix your position X, like let's say where I drew you in the middle of the pool and you don't move, but you let time go forward. And so you're stationary, but waves just keep coming by you. And as they come by you, you keep measuring the height, all right? So in that case, your X would be fixed at a value, maybe X equals 0 or something, right? And then you have a whole bunch of heights of water waves for different times T. And so that's how you could kind of cover the whole situation. To fully describe the water wave at the different locations in the pool, the different X positions in the pool, and at the different times T. So what is it going to equal? Well, we want to be able to handle different amplitudes, meaning different heights of water. If we just had the cos function, we'd be stuck to going between +1 and -1, and not all waves are going to go, perfectly from +1 meter to -1 meter. So we put some number out front A that we multiply by the cos to just scale the amplitude, right? If the water waves went up to 20 centimeters, which is 0.2 meters, then A would be 0.2. What does that mean? Well, imagine you stopped the wave machine and the water was just totally calm. It was just flat. Well, you'd get your ruler and you'd say, well, that flat resting level of the water, that I'm going to call y equals 0. I'm going to call that 0. And then anything above that resting level is going to be positive. Anything below that resting level is going to be negative. So now you've got your kind of 0 position. Then the wave machine starts and you start, measuring heights above that or heights below that. The peak of the wave would be A. So in that example I said before, if the peak is 20 centimeters, A equals 20 centimeters, which is 0.2 meters. Then we have cos. Then we got a bunch of stuff inside of here, all right? Note that we are in meters, which makes sense if we're talking about the height of a water wave. But note that later on, what we're going to be talking about is voltage waves on a transmission line. Since we're talking about voltage, the units are going to be in terms of volts. So let's talk about the stuff inside. Was there a question as it? No? No problem. I just saw your mic was on there. No problem. So let's talk about the stuff inside the parentheses here. Inside here. 2 pi and then little t over big T. What are these things? Well, little t is the same as this little t. That's our time. That's time. Time's going forward. We could kind of stop time like we did with this photograph. That's time. All right. It's a number it's a variable. It can change, and we would want to know what's the height of the water at different times t. But the number on the bottom, the capital T, that's the period of the wave. What does that mean in terms of our water wave? Well, imagine you're standing there in the water and you've got a stopwatch. I gave you a stopwatch and time's going forward. The waves are just washing over you, right? They're just coming down the pool. They're coming down the pool. Right when the peak of the wave got to you, if you hit the start button on your stopwatch, and then you waited until the next wave came, the peak of the next wave, and you stopped it right when the peak of the next wave came. The time that it took to go from the peak of the one wave to the peak of the next wave, which is the same as saying, how long does the wave take to repeat itself? That's the period. That's capital T. So this is just a number, right? That's just a number. So you could look at this as 2 pi, which is one full cycle, one complete, cycle all the way around, or however you want to think about it, like we were saying before. And then if you think about this as little t over big T, what you're really saying is, what fraction of a period is it? Like if little t was equal to big T, then you'd have capital T over capital T and it equals 1. You're a full period. And so what would you be left with? A full 2 pi. What if you were half a period? Well, then your little t would equal capital T over 2. The t's would cancel out and you would have 2 pi over 2. And so you just have pi, which is 180, halfway. Okay. All right, let's look at the next one. 2 pi x over lambda. Lambda is the wavelength. That is the physical distance between the peaks of the wave. So whereas before the capital T is like, how long is it between peak and peak? This is how far is it between the two peaks? And x, as we said before, is the spatial variable, like where are you in the pool? And so once again, we have 2 pi times some fraction. What fraction of a wavelength are you at x? So if you called this like, here is like x equals 0, say, well, once you got to x equals lambda, you would have lambda over lambda, they'd cancel it, and you just have 2 pi because you're repeating yourself again. So that's lambda. Lambda is the wavelength. And the only thing we have left here is this phi 0. And it's just shifts things. So if you imagine this wave in the bottom right, if you just shifted the whole thing to like the right or to the left, that's what this phi 0 would do. We're going to let phi 0 equal 0 first. So if you imagine that, you would have all of this, but if phi 0 equaled 0, then you would just leave it off, right? And you would stop after the 2 pi x over lambda. So we're going to look at that first. Then we're going to add in the phi naught. Phi 0 equals 0. So that's what I just said. And this here is exactly what we just saw, except there was a plus phi 0 before, but that's gone because we had it equal to 0. So if you look at this blue wave on the left and the blue wave on the right, you'd say, well, those are identical. And they are, but they mean different things. So I want you to start thinking about things in terms of position and time. For instance, on the left, this is at time t equals 0. So let's just plug t equals 0 into that equation up top. So we'd have y at x comma 0, right? Because t equals 0. And what would that equal? Well, a is just a cos 2 pi t, but t equals 0. So this one's gone. So all we have is minus 2 pi x divided by lambda. Now, I drew part of the cosine on the previous slide, right? I drew that, but it also comes back here. And what you would notice if when you draw it like this is that cosine is an even function. If you come over to the right a certain amount, that's the same as going to the left by that same amount. What does that mean? Well, if you had your calculator and let's say you were in degree mode and you did the cos of minus 45 degrees, and then you did the cos of plus 45 degrees, they'd be the same. So this negative sign in here, it doesn't matter whether that negative sign's there or not. So cos of, I'll just say some generic thing like cos theta is equal to the cos of minus theta, which means that this is equal to a cos positive 2 pi x over lambda. Okay, this has got no t in it. The only thing that this has in it is an x. So if we wanted to plot it, we would plot it against x. We would let x change. We'd start at x equals 0, right? And when x equals 0, this whole thing goes to 0. The cos of 0 is 1. 1 times a is a. Boom. At x equals 0, the wave is at a. And we plug in, the next value of x. If you plugged in lambda over 2 for x, the lambdas cancel out and the 2's cancel out, and you're just left with pi. The cos of pi is -1. -1 times a is minus a. So that's where that comes from. Now let's look at the one on the right. This one's different. It looks the same, but it's different. So the one on the left, you froze in time. You took a picture. It's basically this scenario in the bottom right. You froze time. You're looking how the wave changes with x. Essentially, we've just plotted that out. The one on the right has frozen your position. Now you're standing in the pool somewhere and time is going forward and the waves are coming over you. So if we plug into our equation, x equals 0, we'd have y at 0 comma t equals a cos. So x equals 0. This equals 0. So this whole term equals 0. All we have is 2 pi t over t. Okay, so if we started at t equals 0, note now we have t. You have to look at your axes here to figure out what you're plotting and what does it physically mean. On the left, it means we've frozen time and we've plotted the height of the wave down the pool. Or if we're on a transmission line, we've stopped time at a particular point and we are showing what the voltage is at different points in the transmission line. On the right, we're letting time go forward, but we've frozen our position. Like, let's say we chose the middle point of the transmission line and we're just there with like our imaginary voltmeter. And as time's going forward and voltage waves are like going down the transmission line, we keep measuring the voltage. It's going up, it's going down, okay? In the pool, you're standing in one place. You got your ruler, you're measuring the waves going up, going down as they pass over you to go from one end of the pool to the other. So instead of things being in terms of wavelengths, they're in terms of the period because we're dealing with time. We're not dealing with distance. Same thing though, if we started at t equals 0, well, that makes this whole thing equal to 0. The cos of 0 is 1. 1 times a is a. So at t equals 0, we're up at a, okay? And everything else is the same too. At half the period, at capital T over 2, when little t equals capital T over 2, you'd plug in capital T over 2 here for this little t. The t's would cancel out, 2 would go to the bottom, you'd have 2 divided by 2, they'd cancel out. You just have the cos of pi. If you're in radian mode and you typed in the cos of pi into your calculator, -1. -1 times a is minus a. That's why we have minus a at time t equals capital T over 2. All right. So they look the same, but they physically mean two different things. Now, what if we took the one case, let's say the left case, where we froze time, right? We froze time at t equals 0. So this one on the left is here at the top right. That's this one up here, time t equals 0, right? T equals 0. What if we, hit, our magical time machine button and we let time move forward a certain amount and then we froze it again? And let's say we did it t equals t divided by 4. That's how long we let it go for. All right, well, we'd use our same equation, right? We'd say y at, what are we plotting against? We're plotting against x, right? So we'd say y at x, comma, t over 4, if we're interested in time t equals quarter of the period. All right, that would be a, that would be cos, it would be 2 pi t over 4 for little t divided by big T, okay? Minus 2 pi x over lambda. All right. Well, you know what? To make life easy for us, let's consider a certain point at x equals 0. Okay. X equals 0. These are all x equals 0. We can say at x equals 0, what do we have? We have y at x comma t over 4, a quarter of a period, is a cos t over 4. So that 4 is going to go to the bottom. So it's going to be 4t on the bottom, and we've got a t up top. So the t's are going to cancel each other out. And we'll be left with 2 pi over 4, which is pi over 2. Okay, I'll just write it. 2 pi t over 4t, t's would cancel out. We'd be left with pi over 2. So then you get your calculator if you wanted, and you plug in, okay, I'm in radian mode. What's the cos of pi over 2? You'd get 0. 0 times a is 0. That's why we're at 0 right there. Okay, what about time t equals t over 2? Well, everything would be the same as this, except that would be t over 2. So the 2 would come to the bottom, so you'd have 2 down there. The 2's would cancel out, and you'd have the cos of pi. The cos of pi is -1. -1 times a is minus a. So you could do this for all the values of x. We just did it for x equals 0. And if you did it for all the values of x, what you'd see is, well, here's our peak at t equals 0. Then you could say, well, where is that peak at time t equals capital T over 4? And you'd say, well, it's here. And where is the peak at half the period? And you go, it's there. It appears to be moving to the right, right? What speed is it moving at? Well, you can see there what it is, but why is it that? Well, remember what speed is. It's always just meters per second, right? It's distance divided by time. So how far has that maximum point moved? Here, we're at x equals 0. Over a period from t equals 0 to t over 2, so over half of a period, we have moved from x equals 0, that's where our peak is, to our peak being at lambda over 2. So remember, we're plotting against x here. That's physical location in meters. Our distance, we want distance over time. How far have we traveled over what time period? How far have we traveled? Lambda over 2. Over what time period? We went from t equals 0 to half of a period. Okay, so the 2's cancel out, and you're just left with lambda over t. UP, we are going to use that for the next 2 months. We are going to use that for the velocity of propagation, also called the phase velocity. You might say, why would we use U for speed, for velocity? Why don't we use V for velocity? That would make sense. Yeah, but very shortly, we're going to be dealing a lot with voltage. So we don't want to use V for that. So we're going to use U. P is for propagation or phase. So UP, phase velocity or propagation velocity. It equals lambda. So whenever you see lambda, it is going to represent the wavelength. That is the physical distance between the peaks. All right, we can go back here. The physical distance between the peaks. Divided by capital T, which is the period. How long does it take for the wave to repeat itself? I'm sure you remember this, that frequency is equal to 1 divided by the period. So we could just rearrange that UP formula, right? Like, look at this, we've got this T in the denominator. So we could write that instead of F, instead with F. So we'll see that shortly. So we got these waves. The waves are given in terms of Y. In this case, it's like the height of a water wave based on its position X and its time T. All right, this is what we just did, saying that UP, if we follow any point P, we would get that UP is lambda over T, which I did it instead of, doing it with dx dt, like with calculus, we did it more intuitively, but it's the same thing. We just did distance over time, okay? And as we saw back here, UP equals lambda over T, right? UP equals lambda over T, and F equals 1 over T. So we could just plug that in. It's got a 1 over T in it, right? So that just turns into UP equals F times lambda, which you might use this to calculate it, or you might use that to calculate lambda. Okay, so you could just rearrange it to calculate for lambda. All right, any questions so far? So we're mathematically describing these waves. We're giving ourselves lots of different ways to potentially mathematically adjust the wave. We can have different A's for different amplitudes. We can look at it at different times. It can have different periods. We can look at it at different positions, and it can have different wavelengths. And we can adjust any of these, or use these variables to accurately represent our particular situation. Okay. All right. So what we just did was what's shown at the top here. Y x comma t equals a cos 2 pi t over t minus 2 pi x over lambda, but we'll sometimes represent it that way, but not as much. Okay. What will we do instead? Well, we'll use that f equals 1 over t. Right, so we could plug that in for that t. So f would just come upstairs because f is 1 over t. So that's what we got here, right? And what is that? That's omega. Omega equals 2 pi f. Remember that one. We're going to use it all the time. And of course, you could also rearrange that in terms of f equals omega divided by 2 pi. I always remember omega equals 2 pi f. I never remember f equals omega over 2 pi. And if you just remember one, you just rearrange it for the other. What about units? Well, the units for frequency, I'm sure you know that it's hertz, right? But what is a hertz? Well, as long as you remember this formula up top here, you can always remember, because capital T is the period. That's the time it takes to repeat itself. So it's in seconds. So this is 1 over seconds. So hertz is 1 over seconds. 2 pi is radians. It's 2 pi radians. So it's 2 pi radians per second. So the units are radians per second. Okay. The units for 2 pi is radians. The units for frequency is 1 over seconds. So you have radians per second. Okay. Going from this one up here, the 2 pi x over lambda, down to here, look, it's still 2 pi x over lambda. This has just been separated from the x because this thing is going to be called something special. It's going to be called beta. And if we plug those in, now we have a simpler representation of our wave. Still have our amplitude A, cos. We got our omega. Omega is just 2 pi f. 2 pi f is just 2 pi, well, 2 pi ft is just 2 pi t over the period capital T. Minus beta x, beta is just 2 pi over lambda. So it's just 2 pi x over lambda. So these are all the same thing. And what did we just see? we had this exact equation. We used this form of it up top here, right? But this form up top is equivalent to this form down here with a negative sign there. That's what we did, right? If I come back here, that negative sign was there. There's a positive sign there. We don't write the positive sign, but it's clearly it's not negative, or we write the negative sign. It's positive. So we found that it was moving to the right, right? When we tracked our position here, boom, boom, we are moving to the right, which is moving in the positive x direction. So we found that this equation means the wave is moving in the positive x direction. Okay. We're gonna see what it looks like when it's moving in the negative x direction in a second. But first here, just a summary of all the things that we've seen. Omega equals 2 pi f. It's the radian frequency, right? The angular velocity, right? How quickly is the angle changing with respect to time? Beta is called the phase constant. It's always 2 pi over lambda. Note the units here. This is one that sometimes students can forget on the midterms and finals. Like, what are the units of beta? So omega is how is the angle changing with time. Beta is how is the angle changing with position, x. Beta is sometimes called the wave number, but I'm going to just stick to the phase constant, I think, pretty much exclusively. If you go on and take ECE 571, which is the follow-on course, then it will more often be called the wave number when you're dealing with plane waves in space where it's lossless, and it might be given the letter K. But for us, I'm going to stick with beta. We're going to stick with phase constant. And Anthony has a question. Go ahead.
I read well, going back to where you have your 2 pi f t
Yep.
minus, okay. I read in the book, which I found very interesting, that if the signs themselves, if they're opposite signs, then the flow is in the positive x direction. However, if they're both the same sign, it goes in the opposite direction, which I could see the negatives. I just had trouble seeing if they're both positive, why does it still go in the x direction? Or, I'm sorry, negative x direction.
Yep, so good question. So I'll jump ahead here. We'll talk about this now. So hopefully I have sold you on this equation representing a movement in the plus x direction, okay? It turns out that you can tell the direction of propagation by the signs in front of these two terms. These two terms being what's in front of the t term and what's in front of the x term, okay? So there's a plus sign here and there's a minus sign there. They're different. It could have been flipped around. There could have been a negative in front of the omega t and a plus in front of the beta x. It would still be movement in the plus x direction. So our rule of thumb here to determine what direction things are propagating in is to look at the signs in front of the t term and in front of the x term. If they're different, meaning one's positive and one's negative, it doesn't matter which one's positive and which one's negative. If they're different, it's going in the plus x direction. Now, what Anthony just asked about was the second case. Down below, I haven't proved this one, or at least it's not as obvious because we didn't draw out these waveforms. So if you want to be fully convinced, and it would be just a good exercise in general, what you could do would be to do the exact same thing as this, these waveforms at the right here, but make this a plus sign, okay? Now, what would that do? All right, well, it would change things a little bit, okay? So what would it do? T equals 0, that one's gonna be the same, okay? So t equals 0 is gonna be the same. The next one, when we have t equals capital T over 4, what's gonna happen is instead of being shifted that direction by, you know, if we think about it in terms of the peak, instead of being shifted there to lambda divided by 4, it's going to be shifted the other way. Okay, so like over here to minus lambda divided by 4. That's where the peak's going to be. Okay. And if you wanted to do that, you could just kind of like plug in different values of x. Okay. So for instance, at the 0 point here, well, they're both going to be 0, whether you shifted it to the left or to the right. But if you look where the peak is, it will be shifted to the other direction. And what you'll find, if you plugged in all your values of x, if you're good with MATLAB, you could do this really easily. What you would find is that the waves have been shifted to the left. And the reason is because you're adding more to it. Because of this plus sign here, whatever 2 pi t over t is, if you add something positive to it, every value in the cosine function is going to come earlier. It's going to be shifted to the left in terms of x, which overall means it's moving to the left. And so if you see that, great. If you don't, I recommend you draw some of these things or plot it in MATLAB, and you'll be able to really, really see it. But basically, our rule of thumb is if the signs are different, like up here, it's moving in the plus x. If they are the same, there and there. In this case, they're both positive, but they could be both negative. And remember that, you know, what I said before, cos of anything, say theta, equals the cos of minus that thing. So if they were both negative down here, well, you just multiplied the whole thing inside the brackets by -1. So it's the same as when it's +1. Okay. This phi 0, which we haven't talked about yet, which we're just about to talk about, it does not adjust the direction. It only is a shift. It shifts it one way or the other, but it doesn't change whether it's going in the plus x direction or the minus x direction. All right. Any other questions about that? Okay, so I skipped something back here. So we have our equations. We got UP. Again, UP is our propagation velocity. How fast is the wave moving? If it's a water wave, how fast is the water wave moving? If it's an electromagnetic wave, how fast is the electromagnetic wave moving? Equals the frequency, which is the number of cycles per second, multiplied by the wavelength, which is the distance in meters from peak to peak of the wave. Now, how did we get from there to there, you might wonder? Well, we defined beta to be this, right? Remember up here, we just said that thing in front of the x, we're going to call it beta. We could rearrange that for lambda, right? Be 2 pi over beta. So we could plug that into there. What would we get? Well, upstairs, we would get 2 pi f, and then we'd still have our beta downstairs. 2 pi f, that's omega. And we still have our beta. So that's why UP equals omega over beta. We're going to have lots of different equations for things. So it's going to be important that you especially keep track of which equations are the generic equations that always apply and which ones are special case equations. These are generic. I'll give you an example right now of the difference between those two. We've seen so far lambda equals c over f. And here, if we solve that for lambda, we would have lambda equals UP over f. C is a special case when, this is when UP equals C. This is the generic one. You can only use this top one if your actual speed that the wave is traveling at is equal to the speed of light. So sometimes we are going to have that simpler case and we'll use lambda equals c over f. But the generic case is lambda equals UP over F. And so you could look at those and you'd be like, I'm confused. Like, what's going on here? That's the difference. Another way you could get confused, let's say you calculated lambda using this, 2 pi over beta. Let's say you had beta. You calculate lambda, right? You get a number in meters. Lambda is always in meters. Then let's say you use this version. You just assumed the speed of light. Well, you'd get 2 different lambdas, maybe. If it isn't actually the speed of light, you'd get 2 different lambdas. And you'd be like, what's going on here? Which one's right? Well, the answer is it wasn't actually traveling at the speed of light, maybe. It was traveling at some other UP. And if you use the proper UP, then this lambda would equal this lambda. So that's just some of the kind of things you'll have to look out for. We're going to have a lot of equations, so it's going to be important to keep them straight. You don't need to memorize them. It's useful to memorize the really simple ones, like, you know, these ones. F equals 1 over t, omega equals 2 pi f. But you're going to have a formula sheet for your exams. The last thing, we have not talked about this phi 0 much yet. So what about it? Well, I had already mentioned it's going to be a shifting to the left or to the right. Doesn't change the frequency. It doesn't change the direction. All it changes is just kind of the position, left to right. So really, if you just remember it's a shift, then all you need to think about is it a shift to the left or to the right, if it's positive or negative, okay? Initially, you might think, oh, if it's plus, then it should get shifted to the right? But it's the opposite, okay? If it's a positive number, if phi 0 is positive, it's a shift to the left. And it's kind of for the same reason that we were just talking about. Like, let's say this peak point here, right? That happens at, okay, we're looking at t. We should always look at our axes, right? So let's ignore the x component temporarily. Let's just say x equals 0 to make our lives easier, okay? Just to simplify our explanation here. So we'll just say, boom, x equals 0, because we're not given any information about x, all right? For this particular drawing down at the bottom. Okay, and we're considering the point, let's just consider the point t equals 0 right here. Okay, so if we plug in t equals 0, then what are we left with? We're left with 0 plus some phi 0. Okay. If phi 0 is positive, then that's going to be some positive number, and we are going to be on our way down. We're past 0, right? We're past 0 in the cosine. We're on our way down. What if, though, you were, let's just say, omega t equaled some, let's say t equaled a small negative value, okay? Such that omega times t was equal to phi 0. So in other words, I'm saying, imagine omega times t was equal to pi over 4. The only way that can happen is a negative t, right? It's got to be a negative number. So if omega times t was minus pi over 4, it'd be the cos of 0. That would be a peak. That would be right there. The other way around, if phi 0 is a negative value, it shifts it to the right. So essentially, if you add a positive thing, every point in your cos function appears earlier because you added something positive to it. If you have a negative thing, everything is delayed. Okay. Okay, so let's put it all together now and do a couple of examples. So we'll probably finish off with these 2 examples. So first things first, what is the amplitude and frequency? What are the amplitude and frequency of these waves? Feel free to say it or to type it in the chat.
Well, the amplitude is 5.
Yep.
Or if you want to say plus and minus 5.
For us, and thanks for bringing that up, whenever we say amplitude, we are going to mean the positive. It's like the
Okay.
magnitude of it. It's the peak. Wherever the peak is, it doesn't matter where the peak occurs. It doesn't matter if it's there or there or there. It's whatever the maximum value is. Okay.
Okay.
So it's
Oh,
just straight up 5. So A equals 5. Okay. Because A, that is what we use to describe our amplitude. Okay. Now we want to get the frequency. Probably easier for this case if you remember F equals 1 over T and you think about what T is.
Yeah, the T is the period before it actually repeats itself.
Yep.
So
what-
looking at this one here, there's a period of 8. I'm sorry, yeah, there's 8. So if you do the 1 over T,
It's 1 over 8. That's all
yeah.
there is to it.
Yeah,
So
it
you
says
look at the
2500,
yeah.
25
you-
millihertz. I don't know.
So it would be 0.125 hertz. So you could say it's 125
Yeah,
millihertz.
exactly.
Yeah.
125 millihertz. Or
Yep. That's right. That's going to be nowhere near the values that we're normally going to be dealing with, but it makes nice, looking at it in terms of 1 second, 2 seconds, 3 seconds, it's kind of easier to kind of imagine it. So this is in hertz. And the way we got that is the red wave is the easiest one to look at, but you can look at any of them. Let's look at the blue one. Take any point. The peak is probably the easiest, but you could choose any, you could choose the minimum as well. That peak for the blue purpley wave occurs at t equals 2 seconds. And the next time it occurs, it's at t equals 10 seconds. So it took 8 seconds before it repeated itself, which meant t equals 8. It took 8 seconds to repeat itself. Now, before we get further into this, if you look at these equations here, they all have an x in them, right? X was our position in the pool or on the transmission line. This is a simpler example. In this example, we only are a function of time. So you can kind of forget about that part for this example. We're kind of doing a simpler example, and then we'll do an example where that has the whole thing, okay? So we are volts in terms of time. So we want to come up with an equation for the red wave. It's going to be volts at a particular time t. So try to come up with this expression for what the voltage is at time t. What do you think? Anybody want to take a stab at it?
5 cosine pi over 4t.
5 cosine. Yes, I'm going to write it a little differently. Okay. I'm going to do, because from back here,
We have the omega.
yeah, I'll even go back all the way to here. We'll
Gotcha.
write it that way. 2 pi t divided by capital T, and we said capital T is 8. So 2 pi t over 8 is how I'll write
Yes,
it, just to make it
capital T
really
is 8.
clear.
Yeah.
Now you could, like was said, you could just say that that's pi t over 4. That's totally fine. And this has units of volts. Okay. All right. Now let's do it for the green and blue waves, and let's do the blue one first.
Blue wave looks to be shifted over 90 degrees. So if we aren't doing phase, this is considering the case 0 where we aren't doing anything with phase.
I'm not going to say that.
Okay. Okay.
If we're considering the case where there's no phase, only the red wave corresponds to that. If there's no phase, and we're dealing with a cos, that means at 0, at t equals 0, it has to be at the peak. and only the red one is at the peak at t equals 0. So there
Okay, so
has to be a phase to
Yeah.
shift it.
So that the red one is the one you're using as your reference and compared to the other waves. And
Exactly. So if I
Okay.
were you, I would do exactly what you just said. Look at the red one and think about what the blue one is in terms of the red one. Like, what do you have to do to the red one to make it into the blue one?
you have to shift it to the left. Well,
You can go either
So
way.
you can go either way. We're going to go the shorter way. We're always going to go the shorter way, but you can always, everything repeats itself over and over, right? So just go the shorter way.
-2?
So which way does it need to be shifted? Does the red wave need to be shifted? Because we want to, we're starting at the red wave, say, and we want to turn it into the blue wave.
oh, okay. Then it's going to be, yeah, 1, 2, 3 to the right. Well,
2 to the
that would be
right,
a
because it's from
negative.
0 to 2.
I'm looking at the peak. I'm sorry. I'm just looking at the peak.
Yeah.
In
Since the peak
terms
is at
of
8. I'm sorry.
okay,
Go ahead. Go ahead.
in terms of phi 0, because that's really what we're playing with when we're shifting it left and right, is phi 0 going to be positive or negative?
Negative.
Everyone agree with that? Or some
Yeah.
people think it might be positive? Because we're starting with the red one, which in this case is like the blue purpley one. We need to
Well-
shift it to the right, which is like going to the green one. So we
Well,
have to have a negative value. Okay.
Yeah.
Okay. So the rest of it, though, is the same. The only difference between the red wave and the blue wave is this phi 0. So everything else is the same. So we have 5 cos 2 pi t over 8. And we just said it's minus something. So now the question is minus what? Now,
Wouldn't that
one
be, go ahead.
One thing you got to
That's a
keep in
direct-
mind is that whenever you're doing the cos of something, the units, like what that thing is in the brackets, the argument of the cosine, it's an angle. And in our case, it should be in radians. Okay. That's what, when you take the cos of something, you're taking the
I'm
cosine
sorry,
of
Professor,
an
I
angle.
hear a delay in your.
Hang on a second. Let me stop my video. And hopefully that helps. Hopefully that helps. Okay. So it needs to be an angle. So you could say, well, what's the purple blue one compared to the red one? And you can say, well, it shifted to the right by 2 seconds. But the way you have to think about this is, what is it in terms of the angle that it shifted to the right? Because it has to be an angle. Remember, 8 is in seconds, t is in seconds. These cancel each other out. You're left with 2 pi radians. This thing over here, the phi 0, needs to be in radians as well.
It looks like it's, is it a quarter pi over 4? Pi over...
Yeah. So how do you get that? Well, a complete cycle is 2 pi, right? So if it was shifted by 8 seconds, it would be shifted by 2 pi. So it's like, what fraction of 2 pi is it shifted? And so what you do is you do the amount it's shifted divided by the period times 2 pi, because that's the fraction of the full period that it's shifted.
I got
So you
pi
would,
over 4.
right. So, well, let's see before I say you're right here. So what would we have? We would have 2 pi. And how much? Because that's the full amount, right? And
Right.
then we're shifted 2 over 8. Okay. So we have 5 cos 2 pi t over 8 minus 2 times 2 is 4. 4 divided by 8, that's 1/2. We have pi over 2. So again, the 2 pi is the full cycle. It's kind of like over here how we're doing, we got 2 pi. And then what fraction of the period are we doing? Over here, we have 2 pi. What fraction of the shift do we have? If it was shifted by 8 seconds, we'd have 8 over 8. That would be 1. We'd be shifted by a full 2 pi. If we were shifted by 4, we'd have 4 over 8. That'd be 1/2. 2 divided by 2, that would be 1. We'd be shifted by pi, which is shifted by 180 degrees, which should make sense because it's inverted, right? It's shifted by 180 degrees. Of course, the other way, you could have just looked at this and written it as 5 sine 2 pi t over 8, right? Because if you look at that blue wave, it is a perfect sine wave. We're normally going to do things in terms of cosines, though. And you could have just looked up what's the relationship between cos and sine in general, and what you would find would be like sine theta equals cos theta minus pi over 2. So you could have done it that way as well. All right, Anthony, question?
Yeah, going back to your equation that uses, yeah, I thought the phase shift was added in the equation that you had on the slide before this one, where you wrote 2 pi over, I'm sorry, 2 pi t over 8 minus 2 pi, and then you multiplied the shift. And I guess, I don't know, I got lost right there.
Okay, just to clarify here, so we're talking about this sign. Is that what you're worried about, or where this came from?
Yeah, no, I understand where the
So it's
2
that
8
minus
came
sign.
from.
Why is that minus? That's the question.
No, it was in your general formula where you had the phase shift was added rather than being multiplied with what I thought.
Oh, because it had a plus phi 0?
Yeah, yes.
Okay, it's plus phi 0, but phi 0 equals a negative number. So we started with our red wave, right? Which is kind of like this reference wave here. And then we needed to move that wave to the right to equal the wave that we're interested in, right? So shifting it to the right means phi 0 is going to be a negative number. So really, if I wanted to be kind of very accurate about it, I would say this whole thing is phi 0. So I could have written that, and maybe I'll like write it over here as v at t equals 5 cos 2 pi t over 8 plus negative pi over 2. Right? Because that's what that is.
Yeah.
Yep.
Thank you.
Yep, no problem. Okay, green wave. Maybe this one will be easy after that. We shall see. So v at t. Same thing, right? It's just shifted. So that's 5 cos 2 pi t over 8 plus or minus.
There'll be another minus.
What do we think? Anyone agree? Disagree?
Plus.
And what does left mean?
No, plus.
Plus.
It should be plus, yeah.
Plus, yeah. So if you look at the red one, to get to the blue one, we have to move to the right, which is a negative phi 0. To get to the green one, the shortest way possible. You might have been thinking, oh, I'm going to shift the whole thing to the right. But if you were to shift the red wave to go all the way to the green wave in this direction, you'd have to go all the way from 0 over to 7, right? We're going the shortest way. It wouldn't be wrong, like it would represent it. But if we're going the shortest way, we would go to the left. Going to the left is positive. And then the question is, what's the actual value? So if we did the same thing we did before, we'd go, well, 2 pi is the whole amount, but we're not the whole 2 pi, because that would be a full 8 seconds. We're only 1/8, because we're shifted to the left by 1 second. So in other words, we're shifted to the left by 1/8 of the period. And the total angle in a whole period is 2 pi. That's why we're 2 pi times 1/8 of the period. And so this is 5 cos 2 pi t over 8 plus pi over 4. Just 2 divided by 8. It's giving us 1 over 4. All right. Let's end off today with this example. The electric field of a traveling electromagnetic wave is given by this thing. So now we're dealing with an electric field. We don't need to know what an electric field really is or anything. We have an equation that describes it. E, capital E for electric field. Uh-oh, we got a Z and a T. T's the same, Z's different. That might be scary. 10. Let's remember our basic form here. A cos omega t. We've got a plus, so it's plus beta z plus phi 0. Now don't be thrown off by this z. We did everything today so far in terms of x. But that was just a distance down the pool or whatever, right? I could have just as easily called that z or y. It just represents a distance, a coordinate system. So if you see, you're only going to see x, y, or z. If you see something other than x, just everywhere in our previous equations that had an x in them, just swap it out for a z. Just think about it as if the z was x or x was z, because it doesn't matter, right? It's just a coordinate system. It's just a direction. It's just your how you have oriented your XYZ Cartesian coordinate system. So don't be thrown off by that. Direction of wave propagation. What direction do you think the wave is propagating in?
The negative z.
Yes. So how did we get that? Remember our rule. We look at the sign of the number in front of the t term and the sign in front of the x, but we're dealing in terms of z. It's just a coordinate, doesn't matter, right? The sign in front of the space or the distance term. In this case, they're both positive. And if we go back to our rule, we said when they're both the same, whether it's both positive or both negative, it means it's traveling in the negative direction, but not negative x, because we're talking about z's instead of x's. It's a negative z direction. If there was a negative sign there, or there was a negative sign there, it would be in the positive z direction. But if both are negative signs, it'd still be negative z direction. Everyone okay with that? How would you get the wave frequency? Think about that for a second.
Well, you could compare omega with that pi times 10 to the 7 t.
Yep, that's
and
how you do
then
it.
Just go through it.
So since it's matched in form, then you can deduce that whatever is multiplied by the t is omega. So omega equals pi times 10 to the 7 radians per second. Now, I always remember omega equals 2 pi f. So you can just rearrange that for f. And there you go. F equals pi times 10 to the 7 divided by 2 pi. Pi's cancel, and you have 10 to the 7 divided by 2, which is 5 times 10 to the 6. Its frequency, so it's hertz, which would more commonly be written as 5 megahertz. Any questions about that one? Okay. Wavelength. Any thoughts on the wavelength?
It goes back to the formula of UP over beta, I think it was.
Okay, okay, so let's say we did that. So lambda equals UP. There's one that's UP over
Well, I'm sorry, it
F
was 2 pi over beta.
equals 2 pi over beta. Okay, and then what?
Well, beta is equal to, let me see here. I think I wrote it down somewhere.
Anyone feel free to jump in, type it in the
Your
chat.
beta is 2 pi over the lambda.
Okay, beta equals 2 pi over lambda. All
And then
right,
since we know beta is pi over 15, these cancel.
Yep.
So we end up with 2 pi over lambda, pi's cancel. Inverse.
so basically what we've done is we used our basic equation, our definition of beta, which was 2 pi over lambda. And we used our basic form of our wave, which has beta times z, meaning all of the
30.
stuff that's being multiplied by beta, sorry, all the stuff that's being multiplied by z is beta. So in other words, beta equals pi over 15. So that's where this equation comes from. Beta, which is pi over 15 from the equation, equals 2 pi over lambda, solve for lambda. So how would you solve for lambda? Well, you could move the lambda over there and bring the pi down there, and the pi's would cancel out, and you bring the 15 over, you end up having 2 times 15. So beta equals 30, and then you need to know the units of beta, radians per meter. You can remember the units from this equation. If you remember, 2 pi is radians, wavelength is always in meters, so radians per meter. So we got the beta right from here, from the form of the equation. Then we used our definition of beta and just solved for lambda. Any question about that one?
Professor, sorry.
Yeah.
I think instead of beta, we should write lambda. Lambda equals 30. No?
Yes. Thank you. Thank you. Yeah, my bad. Let me clean this up. Okay, let me do that again. Okay. Beta does equal pi over 15 from this, right? But we're not trying to find beta. We know beta. I accidentally wrote beta equals, but forget that. We're looking for the wavelength, okay? So we're looking for the wavelength, and the wavelength, well, it equals 2 pi over beta if you want to use this one right here. So 2 pi divided by pi over 15 equals 30 meters. Thanks for catching that. Okay, sorry for confusing it there. So we're looking for lambda. We found lambda by using the beta that was given in the formula. Last one, UP. We want the phase velocity or the propagation velocity, UP. How could we get that? There's a few formulas.
Isn't that frequency times lambda?
That's probably the easiest one. We already calculated F and we calculated lambda, so we might as well use them. F was 5 megahertz. That's 5 times 10 to the 6. Lambda we just calculated to be 30. 5 times 30, that's going to be 150 times 10 to the 6. So that's going to be 1.5 times 10 to the 8 meters per second. Whenever you calculate a UP, you should ask yourself if it makes sense. Okay, if you're dealing with an electromagnetic wave like we were here, because it said it was, it better not be bigger than C. It better not be bigger than 3 times 10 to the 8. Okay, because it can't be faster than the speed of light in a vacuum. It also probably shouldn't be something like 12. Okay. It's going to be something like 10 to the 6, 10 to the 7, 10 to the 8, but not faster than the speed of light. Having said that, though, you could have questions on like the quizzes or something where it's not an electromagnetic wave. It's a water wave or a wave on a string. Those could be 12 meters per second or something like that. So it's only if it's an electromagnetic wave that you need to check it's not faster than the speed of light and it's not kind of really slow. Just to kind of give you a, I don't know, a sanity check when you calculate UP, which we'll be calculating UP pretty regularly. All right, it's 6:45. Do we have any final questions about this example or anything else we covered today?
That's
When
pretty
will
good.
you post your slides?
This has been posted since last week, I think. Oh, you mean the recording?
Oh yeah, you said about a couple of days.
Yeah, I'll probably do it tomorrow. All right, then. Have a good night, and I'll see you on Wednesday at 5:30.
Thank you, Professor. Have a good night.
Good night,
You too.
Professor.
You too. Good night.